Alright, find the volume of solid created by rotating the region bounded by 2y minus x equals 0 and y equals the square root of x around the y-axis. Okay, we're going to follow the same basic steps, but now we're rotating around the vertical axis, and our cross-section is no longer just a disk. Now it's missing a circular part in the center, so it's a washer. So how do you find the area of a washer? Let's talk about that first. What is the area of a washer? So I'm going to kind of do that over here. So a washer is something like this. I know. A washer is just some circular disc with another circle missing in the center. So how do we find the area of this thing? Well, there's two parts. You have this little radius, and you have what we'll call the big radius. And basically, if you have the area of the big circle, let's call that pi, big radius squared, you can subtract the area of the small circle. Let's call that pi, little r squared. And that would equal the area of this washer, just the area on the inside here. Okay, well now that we have a formula for a washer, let's talk about what's going on specifically with this problem. We have two lines here, or two functions, sorry. The first one, if we wanted to get that to a form that we're used to graphing, I could mess with it a little bit. I'm going to make this the red one here. So that would actually, if I move the x the other side, it'd be like 2y equals x, and if I multiply 1/2 to both sides, it would look like y equals 1/2 x, which is a pretty standard line that we've graphed before. So let's kind of just give this a quick sketch, shall we? Okay, y equals 1/2 x. Well, that just means it's going up 1/2. So let's just kind of do this. So it's going to start at 0. It's going to go up 1/2. It's going to go up 1/2. Okay, so there's the first one. This one is the square root of x. This one looks something like this. It also starts at 0. Then it goes to 1, 1. And then at 4, it's at 2. So it looks something like this. Okay. Probably a little bit more curve to it, but whatever, we get the idea that we're looking at this little cross section here. Okay, that's the little area that we're going to find. But remember, we're not just finding that little area, we're actually finding the area of infinite washers rotated around. So when I rotate it around, it looks something like this. I know I'm not that great of an artist, but you get the idea here. And so there's this like weird kind of a conic type shape here that's rotated around the y-axis. And so this is the shape that we're going to find the volume of. I think Saul Kahn does a lot better at drawing these than I do. It's not my best skill, but hopefully you get the idea. It's this weird shape. I'm really horrible at drawing it, but it's basically a bunch of infinite washers revolving around the y-axis. And so what we're really doing is we're really just finding that area in between. When we slice it as a little flat washer through there, we're going to find one of those areas. And then if we can find one of those areas, we can find the volume by taking the integral of that area we just have to think about a couple things. We've got to think about what our radius is. Okay, I talked earlier about the two radius, right? I talked about the big radius and the small radius. So what is our big radius here? Well, it looks like this one, our big radius, I did in red. See, that's the big radius. While this is the small radius. And each of these are just equal, if you think about it, they're just equal to the distance from the y-axis to our function, which we actually can call x, because this distance along here we know as x. So for the small one, we could just say that this equals x. And if we were to solve this equation in terms of x, we would just square both sides, and we'd get that x actually equals y squared. That's important, again, because our cross sections are perpendicular to the y-axis, so we're going to do this all in terms of y. You'll see in a second. And here, if I was to solve this one in terms of x, well, that would be pretty easy. I actually have it up here. It's just 2y equals x. So big R is just x, which is 2y. Okay. All that is to say, now we got to plug this into my formula of, I think I switched the colors here originally. That's okay. Remember, what's really important is that I do the big R minus the small r. And also over here, remember, I can actually factor out a pi, because they both have a pi in them. I could do that too to get my area. So let's go ahead and start writing an equation for just an area of one washer. So what would that look like? It would be the area equals pi parentheses the big radius, which we said is capital R, and we said that's equal to 2y. We want it in terms of y again because our cross section is perpendicular to the y-axis. Okay, so that's going to be 2y squared, because that's just my big radius squared, minus, what was my small radius squared? Well, my small radius squared in terms of y is just y squared. So y squared and then another squared. Okay, I could simplify this a little bit. I could write it as pi 4y squared minus y to the fourth. And then I got to think about what is the limit of these things. Like, obviously we could tell because we know the graph, it starts at 0. So I'm going to take the integral from 0 to something, but when are these two things equal? Well, I mean, I kind of know already. I know from sketching the graph, and I know from knowing the function, but they equal each other again when x is 4 here. And you could see that real quickly, because if I plug in a 4, the square root of 4 is 2. So that's when y equals 2. And if I plug in a 4 here, half of 4 is also 2. So they meet at this point. So this point is 4, 2. But remember, I'm doing the integral with respect to y. So I actually am going to start at 0 and go up to 2 here. That's my integral limit from 0 on the y to 2 on the y. So when I go to write my integral, the volume will equal, pi is just a constant, I can leave it out front, 0 to 2, 4y squared minus y to the fourth dy. And now I'm ready for the math. So let's just go ahead and do it. Let's take the antiderivative. The antiderivative of y squared is y cubed, then divide it by 3, so you get 4/3 y cubed, minus y fourth is y to the fifth, divided by 5, 0 to 2. Let's evaluate this thing. This is pi 4/3 times 2 cubed minus 2 to the fifth over 5. Minus, now if I was to plug a 0 in all these things, 0 cubed is 0 times 4 is 0, minus 0 to the fifth over 5 is still 0. So this is really just like subtracting a big 0, so it's just kind of meaningless. And so let's just go ahead and simplify. I get pi times, well, 4 times 2/3, 2/3 is 8, 4 times 8 is 32, so this is just 32/3 minus 2 to the fifth. Let's see, 2 to the 4th is 16, so 2 to the 5th is 32. So that's 32 fifths. Need common denominator, so I'm going to multiply this by 5, and I'm going to multiply this by 3, and now I get pi times common denominator 15. 32 times 5, let's see, 30 times 5 is 150, plus 2 times 5 is 10, so that's going to be 160 minus 32 times 3. 30 times 3 is 90. 2 times 3 is 6, so that's 96. And what's that? Well, 160 minus 96 is 64 fifteenths pi. And so there's the volume of this horribly drawn solid here. Alright? See you guys on the next part of this video.